All right, guys, this video is going to go over 5.2b notes, which is logarithmic functions part 2. And it's talking about graphing logarithmic functions. We talked about graphing exponential functions in 5.1. Now we're going to do the inverse. Now we're going to do the opposite. Now we're going to do graphing log functions. So it says match each graph with its equation. Here's some graphs. Down here, here's our equations. A is log base 2 of x plus 1. B is log of f of x equals negative log base 2 of x. C is f of x equals log base 2 of x. D is f of x equals log base 2 of negative x. E is f of x equals log base 2 of x plus 1. And last but not least, f is f of x equals negative log base 2 of negative x. So if you notice here, C is going to be our parent function. Log base 2 of x. All of the other ones have a transformation that's happening to log base 2 of x. They all have log base 2 of x. All right, so let's start there. Just like exponentials, logs, it doesn't matter, they're going to have the same shape. It doesn't matter the base, just like we talked about in 5.1 exponentials. So if I go to y equals, let's graph just log of x. Remember, log is right here next to the 7. So log of x. I know we don't have base 2. We'll talk about base 2 in a second, how to put that into our calculator in the future, but it doesn't matter. Just like exponentials, they're all going to have the same shape. All we're doing is matching. So press graph. All right, so our parent, f of x equals log base b. It doesn't matter the base, any number of x. So notice it's going to have this shape. It's going to be like this. Okay, so notice it's going to get super, super close now to the y-axis, but it's not going to touch it. So this time we're going to have a vertical asymptote at x equals 0. Remember, exponentials had a horizontal asymptote at y equals 0. This is the opposite. So now this one's going to have a vertical asymptote at x equals 0. All right, so this graph should be, ready? This one right here. Should be this one right here. All right, so this is going to be C. This is our parent. All right, so then plus 1, going down here, this plus 1 is going to shift it up 1 unit. Remember, it's plus 1 on the outside. Plus 1 on the outside, so it's affecting our y values. Y values go up 1. So taking this graph and shifting it up 1 unit should be this one right here. So this one will be A, shifted up 1 from 1, 0 up to 1, 1. Negative to log base 2 of x. So this negative we know is going to be a reflection about that negative's out front. So it's affecting our y values. So our y values are going to go from positive up here to negative down here. So when we flip our y values from positive up here to negative down here, it's reflecting about our x-axis. So notice I'm not plugging these in because it's a lot easier just to use our transformations to help us. So taking this graph, our parent function, and flipping it over, instead of going up like this, it should be flipped over and be going down like this, which should be this one right here. So this will be our B, flipping it over our y-axis. Sorry, flipping it over our x-axis. Our y values are positive up here, and now they're negative down here. Next, we have log base 2 of negative x. So now I have a negative literally happening to x. It's still a negative, so it's still going to be reflection about. This time our x values are going to go from positive over here to negative over here. So positive to negative x values, notice it's flipping over our y-axis. It's reflection about our y-axis. So taking our graph, instead of going from 1, 0, it'll now be at negative 1, 0. So that'll be this graph right here. So this will be letter D. Last two. Next, we have log base 2 of x plus 1. We're adding. So whenever you add or subtract, it's going to be a shift. It's literally x plus 1, so we know it's affecting our x values. X values are left and right. X values are opposite of what we think. So if we think plus 1, we would think to the right. We're going to actually go to the left 1 unit. So shift to the left 1 unit. So taking our graph and shifting it over 1. So instead of 1, 0, it's going to be at 0, 0. Looks like this graph right here. So that would be E. Taking this original parent, we're always going back to the parent, and we're shifting it over to the over 1. So that means this last one's F, but let's talk about why. So here I have a negative out front. Just like we said up here, negative out front is going to reflect about the x-axis. And we have the negative inside, which is going to be a reflection about the y-axis. So, and we're going to reflect about our y-axis. So both. So now going to our parent. If we flip it over our x-axis, it's going to be from up here to down here. And then flipping it over our y-axis is going to be from down here to over here. So that's where this curve comes into play. We flip it twice. Flip it over the x-axis like we did right here, and then over the y-axis like we did over here. That's what we get this double flipping motion, which is F. So we did it. That is our first page. Okay, so going to our next page. All right, so I'm trying to think of the best way to do this. Let's do this by hand. So graph the 3 following log functions, report the domain and range of all 3. We're going to graph all 3 of them right here. All right, so let's do over here h of x, which is log base 2 of x. So let's do an x and y chart. We just need 2 points. So we know it's going to have that same parent shape. Let's just give us 2 points. We know going back, log base anything of 1 equals 0. So if I plug in 1 for x, that's going to be log base 2 of 1, which is going to give us 0. So 1, 0 is our first point. Over 1, up 0. Our next point could be 2. So log base 2 of 2 will give us 1. That kind of makes it easier for us. So then over 2, up 1. Boom, here's our graph. We know it's going to have this same general shape. So connecting the dots. Great, we know we're going to have a vertical asymptote. Vertical asymptote at x equals 0. All right, so that is h of x in blue. Let me use a different color now. Let's do g of x, which is log base 5 of x. Again, let's do points. Let's plug in 1. So log base 5 of 1. We said log base anything of 1 is going to be 0. So that'll give us the same 1, 0 point. Then let's plug in 5. Log base 5 of 5 will give us 1. So 5, 1 is our next point. All right, so same general shape, connecting the dots. We're going to have that same vertical asymptote. at x equals 0. So no, same shape, it's just kind of like shifted a very little bit because of those numbers, but same general concept. All right, last one, let's do f of x equals log base 7 of x and y. Let's plug in 1, log base 7 of 1 will give us 0. So again, 1, 0. And let's plug in 7, because log base 7 of 7 will give us 1. So over 7 up 1 will give us our next point. So connecting the dots. Here we have the same shape, same vertical asymptote at x equals 0. So our point here with this problem is it's basically the same thing. Our bases change it a very little bit, but it's still the same concept. So here's how you can graph it by hand. Looks scary to graph, but it really wasn't that bad. So domain for all of these, they all have the same domain because they're all going to get super, super close to our vertical asymptote going from left to right. So starting at 0, getting super close but not touching, so a parenthesis, and going on forever to the right. So from 0 with a parenthesis to infinity. Our range is going to go down forever, so negative infinity. It's going to go slowly up forever, so negative infinity to positive infinity. And all three functions have a vertical asymptote at x equals 0. Always put our vertical asymptotes, or asymptotes in general, they're lines, so put them as equations. All right, so here is this page. All right, next page. Use the parent function f of x equals log of x and the transformation techniques to graph g of x, which equals log of negative x plus 4. Also indicate which transformations are applied, determine the domain, range, and vertical asymptotes. Let's see if I can straighten it up a little bit. There we go. All right, so if we know that our parent is f of x equals log of x, and we're looking at g of x, which equals log of negative x plus 4. So we know that plus 4 is going to be a transformation. It's on the outside, so it's going to be affecting our y values, adding and subtracting or shifting. So we know we're going to shift it on the outside, so it's our y values. So it's positive 4, so we're going to shift it up 4. That's r. Then we have this negatives. We know negatives are going to be reflections about. It's negative to x. So that means our x values are literally going to go from positive over here to negative over here. So this is reflecting, or this is flipping over our y-axis. It's reflection about our y-axis, which is n. Those are the two things that are happening to log of x. So those are our two transformations. So now we can graph this thing. We can plug this one into our calculator. So y equals log, which is right here next to 7, of negative x, closing my parentheses, plus 4. Everyone should look like this. Make sure you close your parentheses because it's all we're taking the log of, just like in the problem. Pressing graph. This makes sense. Remember, our parent function from that first page was over here. We've reflected it over our y-axis, so it's over here. And then it went up 4. So that makes good sense. So going to our table, let's find some points. So negative 1, 4. Over negative 1 up 4 is 1 point. Let's see if there's any other points that are good. Let's do negative 10, 5. All right, so connecting the dots. Not very good at drawing, but we kind of can get the point. Remember, there's a vertical asymptote. It's going to get super, super close to this y-axis, but it's not going to touch it. So a vertical asymptote at x equals 0. Flipping it over the y-axis, shifting it up doesn't affect that vertical asymptote, so we're good to go. So our domain, going from left to right, it's going on forever to the left, so negative infinity. It's going to get super, super close to 0, but it's never going to touch it. So 0 with a parenthesis, just like we talked about in 5.1. The only thing is, remember, it was a horizontal asymptote. So the asymptote affected our range for our exponentials. This is the opposite. So now we have a vertical asymptote. It's affecting our domain. Our range, it's going down forever, so negative infinity. Slowly going up forever, so positive infinity. And our vertical asymptote, the equation is x equals 0. Ta-da! That's it for page 17. Page 8, use the function f of x equals log of x again, and transformation techniques to graph h of x equals -3 minus log of x. Also indicate which transformations are applied, determine the domain, range, and vertical asymptote of h. All right, so if we have h of x equals -3 minus the log of x. Now, I've taught this class a lot, so I know people get confused with this problem. That's why I included it in our notes. It might help you to rewrite this as negative log of x minus 3. Let me show you why. So notice this negative log of x is our parent, by the way. This -3, adding and subtracting are going to shift the graph. It's on the outside, so it's affecting our y values. So -3 means we're going to shift it down 3. All right, so down 3, which is y. Then we have this negative out front. So negative out front are going to reflect. Negatives in general are going to be reflections. About it's out front, so it's affecting our y value. So looking at our graph, our y values go from positive up here to negative down here. From positive to negative are reflecting. We're flipping over this x-axis. So reflect about our x-axis, which is z. So those are the two things. So for me, it's easier to see it in this form than in this form. Personal preference, same thing, but this helps me, so maybe it'll help you. So there are two transformations. So we're taking our graph, we're shifting it down, and we're flipping it over the y-axis. We could plug this into our calculator again. So y equals, I know I need to charge it, I'm working on it. -3 minus log of x. By the way, you could put in this one too, doesn't matter, they're the same thing. -3 minus log of x. Going to our graph. Yeah, so it should be over here. I'm sorry, down here. I think I said over here. I don't know, whatever. But our graph was going back to our parent. Let me go back one more page. Remember, this was our parent. So flipping over our x-axis would be from up here to down here, and then we're shifting it down 3. So here we are. Going to our table. Errors because nothing's going on there. Let's put this first one, 1, -3. Is there another good point? 10, 4. 10 up 4. Bingo. So graphing this. -10, -4. This is when my whiteout would come in really handy if it would be working. All right. Forget it. This one. Exit this one out. All right, so our graph should look something like this because it flipped. Our vertical asymptote still staying the same. It's still going to get super, super close to our y-axis at x equals 0, but it's not going to touch it. All right. So our domain, going from left to right, it's going to get super, super close to 0, but not touch it. So 0 with the parenthesis. On forever to the right to positive infinity. Our range, our graph is going slowly down forever, so negative infinity. And then it's also going up forever, so positive infinity. And our vertical asymptote is at x equals 0 still. Another one down. Last one like this. Yeah, last one like this. So sketch the graph of f of x equals 10 of x. This is our exponential. And g of x, which is log base 10 of x, which is the opposite. So it's inverse and exponential form. Notice are both base 10. On the same set of axes, so on the same graph, also graph the identity function, which is h of x equals x. Take note of the symmetry of the solution. Report domain and range of f and g. Note, like we talked about, f and g are inverses. Do you recall the relationship between the domain and range? Do you recall the relationship between the graphs of the pair of inverses? Okay, let's talk about that in a second. Let's do one thing at a time. So if we have f of x equals f of x equals 10 to the x power. All right, so y equals 10 to the x power. Oops. Pressing graph. We know it should, going from 5.1, have that shape, that curvature shape. Let's go to our tables to get some points. Okay, so we have 0, 1. And 110. All right, so going back to our graph, it's going to have this shape. You remember it's going to get super, super close to our x-axis, but not touch it. So we have a horizontal asymptote, which I'm going to label as HA at y equals 0. So that's f of x equals 10x. All right, so let's do another color. Let's do g of x, which is log base 10 of x. Remember, log base 10 is just common log, so just log of x. So y equals log of x, pressing graph. We know it's going to have this shape with the vertical asymptote. Let's go ahead and draw that vertical asymptote. At x equals 0, getting super, super close to x equals 0, but not touching it. Let's go to our table to get some good points. So over 1 up 0. And then let's see another one, 10, 1, over 10 up 1. Here is our shape connecting the dots. Ta-da! They're opposites, so it should be flipped. They are. It's so nice. All right, our last thing that we're going to graph, h of x, which is our identity function. H of x is just x. So just to kind of stay consistent. So plugging in just x to y equals, going to our graph, it's going to be the identity function, which is a diagonal line. Whenever it's talking about the identity function, that means whenever you go to your table, x is the same as y. So 0, 0, 1, 1, 2, 2, so on and so forth. So let's connect the dots here. So this will give us h of x. This one was g of x. So if you notice, if I were to take my graph and fold it on h of x, fold it on that identity function, it's going to be the same thing on both sides. So what do you recall about the relationship between the graphs of inverse functions? They are symmetrical. They are symmetrical about the identity function. So if I fold it diagonally, it'll be the same on both sides, which is what's happening here. So it's kind of cool. So what is the domain of f? So f is our blue function, our exponential. Our domain is going on forever to the left, so negative infinity. And it's slowly going over to the right, positive infinity. What's the range of x? So it's going to get super, super close to 0, but not touch it. So 0 with a parenthesis, and then going up forever to infinity. Now talking about g, so now talking about the pink function. Domain, from left to right, it's going to get super, super close to 0, but not touch it. So 0 with the parenthesis, on forever to the right to pos infinity. And the range of g, so it's going to go down forever, so neg infinity. It's going to slowly go up forever, pos infinity. So what do you recall about the relationship between a domain and range of inverses? Remember the domain, if you notice, of f, neg infinity, pos infinity, is the same thing as the range of g, because they're flipped, x and y is flipped. Likewise, the range of f is going to be the same as the domain of g. We swapped x and y, that means we're going to swap our domain and range. Ta-da! Done with page 19. All right. Last page. Determine the domain of each of the following functions. Report the solution in interval notation. Also identify the equation of the vertical asymptote of each function. All right, so if you notice, going back to our parent, let me go back to that page. Here's the parent talk about the log functions. So notice it's going from 0 to infinity. So not touching 0. So notice our x values are only positive. That means I can only take the log of a positive number. I can only plug in a positive number for x. I only get a positive number out for our domain. So whatever we're taking the log of has to be positive. So here if I have h of x equals log of negative 3x plus 6. So whatever we're taking the log of, which in this case is negative 3x plus 6, it has to be positive. It has to be greater than 0. Because that's what our, going back to our parent, that's what our domain was. It's going from 0, not including 0, so not or equals to, and everything bigger. So whatever we're taking the log of, set greater than 0. Let's get x by itself. So let's subtract 6 from both sides. That way those cancel. Negative 3x is greater than negative 6. Let's divide both sides by negative 3. That way those cancel. Notice we're dividing by a negative, so don't forget to flip the sign. Flip the sign when we multiply or divide by a negative number. Here I'm dividing by negative 3, so we're going to flip the sign. So now we have x is less than positive 2. All right, so putting this on a number line real quick to put it in interval notation. Our number line goes from negative infinity to positive infinity. We're talking about positive 2. We're saying x is less than 2, so everything on the left-hand side. Not including 2, so open circle. So our domain is from negative infinity to 2 with a parenthesis. All right, so last thing, also identify the vertical asymptote. So going back to our parent function, our vertical asymptote was at that 0. Remember, we're getting it close to 0, but not touching it, so x equals 0. So in this case, our vertical asymptote is going to be at 2. It's going to get super, super close to 2, but not touch it. So our vertical asymptote, it's always the number here, is going to be the equation x equals positive 2. Done. So again, whatever we're taking the log of, we're going to always set it greater than 0, solve it, put it in interval notation, and that number is what's going to give us our vertical asymptote. Let's do another one. Oh, here is our answer. So our domain is from negative infinity to 2 with a parenthesis. So the function h has a vertical asymptote at x equals 2. I'm really doing a great job here. So same thing for the next one. G of x equals log base 6 over 7 of 12 plus 4x. Notice I don't even care what the base is. It doesn't even matter. I'm just whatever we're taking the log of, which in this case is 12 plus 4x, has to be positive. It has to be greater than 0. Now we can get x by itself. So let's subtract 12 from both sides. 12 minus 12 cancels out. We're left over with 4x is greater than negative 12. Getting x by itself, we can divide both sides by +4. So because we're dividing by +4, our sign's going to stay the same. So x has to be greater than -12 divided by 4, which is -3. So putting this on our number line from -infinity to +infinity, we're talking about -3. It's just greater than, so it's going to be an open circle. So x is greater than, so everything to the right. So our graph's going from -3, not including -3, so a parenthesis, to +infinity. So that is our domain. Oh, sorry. So now using this, my vertical asymptote is going to be at the equation x equals -3. Done. It's going to get super, super close to that vertical asymptote at -3, but it's not going to touch it. Last one, if we have ln of x squared plus 2x. So it doesn't matter what our base is, whatever we're taking the log of, which in this case is x squared plus 2x, has to be greater than 0. All right, so x squared plus 2x squared, so that means I have to factor this thing. If I factor it, my first step in factoring is GCF, x squared plus 2x. I can take out that GCF of x. We're left over with x plus 2 is greater than 0. Remember, this is the same thing going back to the end of test 3. I want my critical values. So setting them both equal to 0, x equals 0, and x plus 2 equals 0. Getting x by itself, I have x equals 0, and x equals -2. Remember, it's an inequality with x squared. So that means I'm going to go, I don't know why I'm whispering, but I'm going to go to my number line from -infinity to +infinity. I have -2 and 0. Remember, those are the points on my number line. Just greater than, so they're going to be both open circles. Remember, I have to test all these points now. So testing from -infinity to -2, let's do x equals -3. So -3 squared plus 2 times -3, is that greater than 0? -3 in parentheses squared plus 2 times -3 will give us 3. 3 is greater than 0, so this side works. In between -2 and 0, let's test x equals -1. So -1 squared plus 2 times -1, is that greater than 0? So in parentheses, -1 squared plus 2 times -1, and that will give us -1. -1 is not greater than 0, so that middle section does not work. Last thing, let's test in between 0 and infinity. Let's test x equals +1. So if we have 1 squared plus 2 times 1, is that greater than 0? Oops. 1 squared plus 2 times 1, that will give us 3. 3 is greater than 0, yes, so this piece also works. So, all right, so now our domain is these two pieces. So from -infinity to -2, or it could be from 0 to infinity. Notice open circles, so notice the parentheses. All right, and then vertical asymptotes, we have 2 different pieces now. So putting those 2 pieces in our vertical asymptotes, so x equals -2 and x equals 0. So those are our 2 pieces. I want to show you on the graph what it'll look like too. So if we were to graph this thing, let's go to y equals ln of x squared plus 2x, pressing our graph. There's one piece. Oops. Here's our vertical asymptote at -2. Oh no. And then here's our other vertical asymptote at 0. So kind of cool. All right. So is that it for this section? Yep, that is it for 5.2b. Thank you for watching. If you have any questions, please let me know.